Okay, attention please. If you see Blackboard, you can see that we have set up few of these big boards in the lab. So this week you will be using internet to connect the boards. So we'll teach you how this week today, and I will reorganize this stuff after 44 seconds. And okay, so yes. As some of you must already know, we actually had this course before 2022. We got some feedback from students that it would be nice if we have some introduction before we do this lab session. So can anybody hear my voice correctly? Can you read? Great, okay. So as Professor mentioned, we have our course schedule. Okay, what can't I see anything? We have uploaded our course schedule in Blackboard. You may have seen this. So on the schedule, we have labs every Friday. And until lab 6, we will have one assignment for each week. And the assignment is basically reviewing the stuff we have coded in the lab session. The deadline should be Thursday, right before the next week. So which means that today's assignment due is next Thursday midnight. Okay. And rest of the so until the lab 6, we will teach you HLS, how to code your own hardware in like C++ like Azure. And the other half, we actually teach you nothing, but students will have time over a month to focus on their final project. You guys have some sense about what we're going to do in our final project, right? So for the last of the half of the semester, we will just gather here and just discuss about what we have done. And the only objective of this course is to finish your final project. Please don't care about anything else. Just focus on finishing your projects, okay? So today, this lab will be easiest lab among the 6 labs. But unfortunately, this is the period where the most students drop. Okay, so today what we're going to do is, we will make a fully functional SoC attached with the FFT accelerator. So, question like, is there any students who do not know what an FPGA is? I have never heard of an FPGA in my life. Please raise your hand. Okay, good. I prepared an introduction. And today I want to discuss about 2 things about hardware design and SoCs before I start the lab session. So what's an SoC? The computer science majors here? Bingo? What's the difference between a CPU and an SoC? You don't know? Okay, what do you want? What's the difference between a CPU and an SoC? I don't know. Okay, so SoC is basically a systems on chip. A system on a chip. So let's say you have a CPU. You have a CPU. Well, but it's a CPU, it's not a fully functioning computer. I mean that we can't watch Netflix with just the CPU, right? So in order to make this into a computer, what do you need? We need some motherboards, and we put some like GPUs, RAM and stuff. And then you can like watch Netflix. But imagine that we all put every of the components into a single chip. That's exactly the concept of an SoC. Right here, this is one of the diagram of the latest Snapdragon processor, which is basically inside Android phones. And you can see that we have CPUs with a GPU and even an NPU. And we have like DRAM controllers, memory, I/O, Wi-Fi, modem, whatever. So basically an SoC is something more than just the CPU. And inside of the SoC, the main components are you have an NPU, a bunch of CPU, GPUs. Nowadays, there are fancy accelerators and NPUs. And most importantly, if you have multiple components on a chip, what do you need? You need an interconnect. An interconnect that lets the components able to transmit data to each other. And often we have sometimes some modems like for the Wi-Fi or stuff. We even have some analog components, power management units. Sometimes with the DRAM, you see like after the M1 processor, they actually have a DRAM inside the chip. Actually, a package of it. So in this course, we will focus on these three things. First, the CPU, which is already built inside our boards. And the second is an NPU, which is sort of again an accelerator, and we're gonna make it ourselves in HLS. Lastly, one of the most important part is the interconnect. How do we make components conversate to each other in an efficient manner? So the question is, how on earth are we going to make it design in a single semester? Well, so we have two big questions. First is, how do we code the hardware? Well, this is about HLS, and we're going to start talking next week. But how do we even verify the design? Let's say we have coded and made some sort of SoC hardware. And how do we test it? I mean, we can't just like go to Samsung and ask to make a chip, right? So we need a way to fast prototype a hardware easily. And this is why we need FPGAs. Well, I'm pretty sure if you have learned like digital logic or so, you may have experience on using FPGAs. But in case you're not, FPGA is a field programmable gate arrays. A field of programmable gate arrays. And when I say gates, it's gates in digital logic. You can think of these gates as AND or NOT gates. So we have a bunch of millions of gate arrays, and we can assign these gates. You should act as an AND gate. You should act as an OR gate. A bunch of these will act as an AND gate. And we connect them in some sort of, I don't know, like very nice manner. We can basically program an FPGA to work as any sort of digital design possible. If you want an FPGA to work as a CPU, you can. If you want it to be an FPU, you can actually make it. So in this course, we will give you boards, FPGA boards. In special, we are going to use the Zinc series FPGA. The cool thing about this particular FPGA is that on the chip, we already have a working ARM processor, and they are connected to a programmable logic, which is basically an FPGA. So let's say we want to build an SoC system on chip. We already have a working CPU here. That's nice. This will make our development life easier. Okay, this is the chip.
So what else maybe show this to the student? So okay. So this is the, you see the color, the pink board. That's why it's called pink. But also it means Python something, Python plus pink. But pink. So on the flip side, there is not much. Most of the things are here, and what's I think this is a video, right?
Yeah, this is the FPGA, and this is
You can have
small chip.
Yeah.
So over here, and we have a bunch of here, and this big board is actually one of the cheapest board you can get on the market, and it's usually you can use it like on fancy audio. So you have a bunch of I/O pins. Actually, in our lab, Minsung is using this to do some ReRAM or other like fancy experiments. So not this week, but starting next week, we will give you this board for each groups, so we can use it.
But right now, there are a bunch of these boards somewhere, and you can remotely access these boards through Synchron. So you need to have connection, to access this.
So great. So why are we using this particular board? So I know there are some CS major students who actually heard operating systems and system programming course, right? The problem of making a custom hardware is that if you ever make a new hardware, you need to rewrite the software in scratch. You need to write the operating system, drivers, compilers, and so on. But that takes too long, right? The best thing about this board is that it lets you use your custom hardware on Python. Wow. That's amazing for me. I guess you guys will not feel the big difference, but anyway, we had put a lot of effort to make this course easier, and we will use Pinboard and we will use Python, so we can only focus on our DLL accelerator design. Okay, so any questions so far? No? Great. So I believe I have addressed the second question. And how about the first question? How do you code a hardware? Well, in reality, designing a full SoC takes millions of code. It takes months and years of effort. And it's almost impossible to do this in a single semester. So how do we going to make this doable? Well, one fancy way is that most of the SoC design nowadays are based on IP-based design. IP meaning that vendors, you can think of like Qualcomm, ARM, famous companies, they provide CPU or hardware blocks as IP. You can see IPs here. This is the CPU IP. They're like interconnect IPs, DMA IPs. And if you have bought an IP yourself, you can simply wire and connect them together to make a fully functional system. So you can actually look up on that link to figure out what kind of IP we have. And today's goal is that Vivado provides an FFT accelerator IP by default. We were going to make use of them, meaning that we will do no hardware coding this week. We will just, as a tutorial, we are just trying to learn how to use Vivado and FPGA boards. We will wire up the components together to make an SoC and verify that using Python. So today's goal, going back, is that this is the block IP design, which we are going to make it today. And you want to make a fully functional SoC attached with the FFT accelerator. And I figured out that my previous in the previous course back in 2022, actually CS students did not know what an FFT is. So I prepared a very short introduction on FFT. Any EE students? Great, what's an FFT? Fourier transform? Fourier transform. Fourier transform is basically a computation which takes n complex numbers, an array of complex numbers, and it transforms into another n array of complex numbers. And the fast Fourier transform is an algorithm to compute this Fourier transform in an n log n time complexity. And I know some of the EE students heard like digital signal processing or like what's called TNC. And you see that FFT is very crucial in signal processing. And that's why in most of our smartphone SoC, we always see an FFT accelerator inside it. So, okay, so we know what an FFT is. We know how to do an IP-based block design. So what kind of IPs are actually needed on today's lab session? Well, of course, we need the CPU, which we already have. And then we also need the FFT accelerator, which Xilinx gives to us by default. And I said that in our lab, we will be looking upon three important components of an SoC. And there's one thing that hasn't appeared here. What's that? So an SoC does not work in only these two items. What do we need more? In this course, if you have any questions or if you have something you do not understand, please tell me right away, okay? So we need CPU and FFT accelerator, and we need some interconnect so we can wire them up together. But on most of the memory-intensive accelerators, the interconnect is not enough. We need a new component, which is the DMA to direct memory access. You heard the operating system. No, Ron? You heard of it, right? No? Seriously? Okay, nobody heard operating system first? Okay, so what's the DMA? You know what the DMA is? Okay, so basically, it's usually the CPU's job to read data from the DRAM and copy that to another location, right? But usually copying data from the DRAM to another place takes a really long amount of time. And we don't want to waste CPU cycles for doing that. So one turnaround is that instead of asking CPU to copy memory, we can add another hardware block that can actually have the functionality to read and write memory from the DRAM. So we can copy the data from the DRAM to the FFT. Do you understand? Basically, we will not ask the CPU to copy data from the DRAM, but we will have a dedicated new hardware unit that is possible to copy data on its own. So this is actually one of the most crucial components in boosting your accelerator designs. And the expected outcome today looks something like this. We have the processor at the below, and we have the AXI interconnect, which will gather all the components together. We have the FFT accelerator, and we have 3 DMAs to couple them together. Okay, this is the introduction I have prepared so far. Any questions? Okay.
Questions? Do you really have questions about this? I think I have a ton of questions about it.
Okay, first, I have only one rule in the lab session. If you have questions, ask me directly. Do not hesitate, okay? So I will show you how to use Vado starting now. And if you have any question and you get stuck, you will never be able to finish it on time. So if you have questions, do ask me right now.
In here, here, from now on, if you miss a few steps, then you can install again. You will not be able to do very well. So try to be very attentive and make sure that you follow the instructions. So, and we have a couple of TAs actually here and so if you have problems, questions, raise your hand. There's another TA right there. So we have many TAs there.
Okay. I actually need more coffee. Anyway, is there any student who do not have Vivado installed right now? Is there any student who missed a step in installing Vivado? For example, I didn't include the board button. If you have math questions, please ask me. Okay. Okay.
So
what is interconnect? It's a very nice, awesome question. Okay. So this is what today's MCC looks like. You have a bunch of CPUs. And CPUs, you have a lot of in and out data. And how are you going to connect them? How do you connect them? So there's a very important concept in data computer architecture that is called data coherence. Meaning that you have a bunch of CPUs. And if you want to write the same location of data at once, every of the CPU will see a different copy of the same data, which will be a problem, right? You want all the cores to look at the same memory in a very coherent fashion. Do you understand? Okay. Do I have a pen? Okay. We're basically talking about multi-cores or like SoCs with a lot of components. You get that, right? So let's say you have some memory in a DRAM. And let's say you have some data. And there's a CPU and a Fourier transform accelerator. The CPU reads the data. And let's say it do some operation, I don't know, like add something, multiply something, and the data changes. And the Fourier transform will do the same. So right now, you have read the same data, but these two components did their processing of their own. So do they know each other's data? No. So we need to synchronize every component so that they're looking at the same data, right? That's the main reason why we have complicated interconnects. We want to make high-speed data transmission between components, and at the same time, we want to make it coherent. Okay, great. Any other questions? Great, let's get started. So open up Vivalo. We'll create a project. Start by creating a project. Well, the location doesn't matter, but please do not include Hangul inside the location. And because we are obviously making 100, can you look the screen? So is it big enough to read the screen? Is the screen big enough to read? Okay. So we will gonna make our project, and I promise you, we will not do any harder coding on this lecture. So we will not specify any kind of source at this time. And then if you follow the instructions correctly according to the blackboard, you will see the pink Z2 board. We will do it right now. Yes, the board? Yes. Is there any students who cannot find the board on your board list? Wait. Okay. Works? Why not? If it does not work, please tell me. Okay. Okay, attention. Let's get back to work. So, we made a project. Get started. So as I mentioned before, main methodology is the IP-based block design. So if you see on this tab, you will look at the create block design. Just press create block design and name it whatever you want. I really need to sit down at this moment. Okay, so we can draw the block diagram here. And let's start by adding the first component, which is the Jing processing system, the CPU. If you press the plus sign and write down zinc, you can add this. And then we will add the second important component, which is the FFT. If you search for FFT, you will find the fast Fourier transform. Anybody stuck? Yes. Great. Looks like everybody's on the same point. So, if you double click the FFT IP like this, you can actually configure the IP to whatever usage you want. Which is taking really slow. Okay, we have it. So, I believe most of the students were back at Wednesday's class, this Wednesday, 2 days ago. We talked about programmability. We want our IP to be programmable. Programmable in the sense that you want to have the ability to run different lengths of FFTs. So I will just turn on the runtime configurable transform length. If you click it, it will just lag and wait for a minute. Let's take some rest. Okay, it's on check. And the transform length, because we have set the runtime configurable transform length, this actually will be the maximum transformation length. And we will push this limit up to 16K. Work. Why is it not working? Okay. You set these two. And if you go to the implementation tab, which is still lagging. So I told you that an FFT takes n complex numbers as inputs. And the problem is, how do we represent complex numbers? WD students, does anybody does not know about floating points? Everybody knows floating points, right? This is the way how we represent decimal points on CPU. But the problem of floating points is that they're expensive. Expensive in the term that it takes up too much harder area. Too much harder area means that a larger die, a larger chip, which will eventually be expensive. So in normal cases, it's very common on hardware accelerators to use a custom data type. So in this case, you can see we are using a fixed point data format, not a floating point. And we will use 16 bits for the imaginary part and also the real part. So instead of using 32 bits for one FP32 value, 14.32 bit value, we will chop the 32 bits into two parts of 16 bits, each representing the real part and the imaginary part of the complex numbers. So you should remember this because on the assignment, I will ask you to correctly decode this on Python. And we have a bunch of other options, but we want the total length to be 32 bits, so we'll just leave it as it is. And if you go back to configuration, yes, it is pipelined streaming I/O. Usually, there's a trade-off in computer hardware design is that if you want a high-performance design, you can use more hardware area, but it will be costly. So the pipeline streaming I/O is actually the highest performance design, which actually takes more area than other settings such as radix 4 or whatever. Okay, it seems that we have set the transformation length, architecture choice to pipeline, and the runtime configurable length, 3 things. I think we're done. Let's press OK. And as I mentioned before, we have one more very important component, which is DMA and the interconnect. So we'll start by adding DMA. So if you see on this IP, if you look closely, we have 3 ports that has the name AXIS. AXI is a protocol for interconnects that are used on ARM devices. So AXI is just a vendor name. S stands for stream, which is basically the DMA stream that pushes a lot of data from the SRAM to this component. Which means that in order to use this design, we need 3 DMAs, 2 for input, 1 for output. So we will have 1 DMA for input data, another DMA for output data, and lastly, a third DMA to configure the length of the Fourier transform we want to do. So we will start by adding 1 DMA controller here. Just press the plus sign and search for DMA, and you will find the AXI direct memory access, not the central memory access, the direct memory access. Okay, we have a somehow looking design like this. We have a bunch of control signals, and let's configure it. Are we on the same page? Are we on the same page? Okay, good. So on the configurations, you will see the enable scatter gather, which is a fancy feature, but we will not going to use it. So let's turn it off. Do you remember what was the max transformation length of the FFT device? What was the max transformation length? 16K. In number of bits, 16K is 2 to the power of 14. So we need a larger buffer than the 2 to the power of 14 to store them. So I will just boost this number of bits into 18. So we have plenty enough space to store the data. And the first DMA we're going to use is to enable write commands. Write meaning DRAM writes. So from the FFT accelerator's perspective, it will be data out. Data out from the accelerator and data write to the DRAM. So I will just disable the read channel by now. Just like intermediation. Yeah. Okay. So the 18 bits means that the width of the buffer entrance in our FFT, we need to store of the 16K 32-bit values. And the data length is 32-bit for bytes. And we need 16K width to store the complete data. Q to the power of 14 is 16K. And we need a buffer large enough to contain all data. So that's why I'm just setting 18 here. Something that is way harder than 4. Okay. Okay, great. Looks like we're on the same page again. Let's click OK. Oh, and we have a smaller set of wires. If you look at the name of the wires in details, you will see AXIS with an SAXIS and an NAXIS. They each correspond to a master and a slave. In an interconnect, a single master will be connected to a slave. The master's responsibility is to say, hey, I will send the data now. And right after, the slave will respond, okay, I'm prepared to get some data. And then the master will be actually sending the data. This is called a handshake and how interconnects work as a very basic level. So basically what I'm telling you is that NAXI will be connected to a SAXI. And if you see the FFT IP, the data output is the NAXI, which should be connected to the SAXIS. If you click on this, you can see a single little pen, and Vivado will automatically let you connect to the corresponding port. So we can connect it like this. So since we have made the right DMA channel, we also need to make read DMA channels. In this case, 2 read DMA channels. Let's make it. We'll also disable scatter gather and make the buffer length at 18 bits and disable the write channel. So in our case, the FFT IP is always 32 bits. We don't have to care about this. It's already aligned at 32 bits. I know Vivado IP block design kind of sucks. If you press the refresh, it will make it neat and tidy. So, since this is a read channel, we have the MAXIS, which is the master AXI. This will be connected to the SAXI data. And right here, you need to remember that the data out is connected to the DMA 0. You need to remember that later on when we use Python. And we have one single leftover port, which is the config port. This will store a single integer that let us configure or program the device to act as an n-length Fourier transform. So for this AXI config, we'll make a small DMA. The minimum bits is 8, so we'll just make 8 to just reduce some hardware resources. And in the same fashion, I'll just disable the write channel. Connect it. And we now again have the master AXI stream port, which we can connect it to the slave AXI stream config port. Everybody done? Should look like this. Okay. So we have made the DMAs, meaning that the FFT IP has the capability to read and write from the DRAM. But the problem is, the FFT IP is not yet connected to the CPU. So in order to connect to the CPU, what do we need? What do we need? Interconnect, correct. Finally, so we will search for an AXI interconnect. We have this AXI interconnect here. So in this AXI interconnect, we need to make two interconnects. The first interconnect will be responsible of CPU controlling all the DMAs. And we have a second interconnect that will have the DMAs being able to talk to the CPU. So first, we will make an AXI interconnect, double click it, and we will make it as a single slave, whose the master will be the CPU. And we will have 3 masters so that it can control the DMA. Just refresh. And the slave AXI will be connected to the master AXI general purpose 0 of CPU. Meaning that the CPU can now control the DMA. That's good. So the other 3 master ports of this AXI interconnect will be connected to, very straightforward, right? Okay, first, we create an AXI interconnect. And the slave of the AXI interconnect will be connected to the master of the CPU. And then we have 3 more masters on the AXI interconnect. These will be each connected to the slave port of the DMA, like this. Are we on the same page? Yes or no? Yes. Okay. So the CPU can talk to the DMAs right now. It can ask requests like, hey, send some data from where to whatever and so on. But we don't have the capability for the DMAs talking back to the CPU. They need to talk back to the CPU that, oh, we finished our job. That's why we need an extra AXI interconnect. Because this AXI interconnect acts the complete opposite, now we will have 3 slaves and a single master. And each slave will be connected to the master port of the each DMAs. Where do I have it? Great. Yes. Okay, sure. The first AXI connect is we want to make the CPU talk to the DMAs. The second AXI interconnect does the right opposite. It lets the DMA being able to talk back to the CPUs. So that's why the first AXI interconnect has one slave and 3 masters. Instead, the second one will have 3 slaves and 1 master. So I configured the second AXI interconnect to have 3 slave ports and a single master. And you see, each of the slave of the second AXI interconnect connects to the DMA. So at this point, we will see no more missing wires except for this one. I think this is probably about the 2021, but 2020, I don't know why. But at this moment, except for only leaving that open, we need to run block automation and connection automation. You see, some of the little wires, they can be connected automatically by Vivado. So we will just run connection block automation. And if you run block automation, yes, the fixed IO correspond to these Arduino-like pins on the board, and the DDR will be automatically connected to the DRAMs on the board. That's great. We still have leftover small wires. This can be connected by run connection automation. Run connection automation and press all. Okay. And you'll automatically connect. In details, the actual job the run connection automation is doing is connecting these wires, which is mostly clock signals, reset. If you ever heard digital logic, these are the clock, reset, acknowledge, whatever. And because it does this for me. Yeah. Yes, true. That's a fascinating question. Do we need to keep track of the ordering when you connect these wires? Can you mess up with them? That's true. That does not matter. Because the AXI interconnect is in fact an MMIO device, memory mapped IO. If you're not a computer science major, you think what the hell is an MMIO? But basically an MMIO means that the CPU will talk to these devices in a certain memory location. That's why the wiring here is not important. It is only the memory mapping that is important. And we will going to actually do that. So are we done? Connection automation, are we done? So before we run this, we still see a dangling port here. It's not connected. And this port needs to be connected to the CPU. This is the master AXI, which means that we need a slave AXI on the CPU side. But if we see the CPU, we don't have a slave AXI. What the hell? Well, we need to make it. This is what our CPU looks like. It's actually a small SoC. We have dual core. We have cache, SRAM. We actually have an interconnect inside the CPU. And whatever. We need to make use of the FPGA logic to make a new slave AXI port. You can do this by the PSPL configuration, which is the CPU FPGA connection. HP is not Hewlett Packard, it's high performance. We will enable the SAXI high performance 0 port. If you do this, voila, we have a new port here. Well, the Vivado kind of complains you have different clock, whatever, but we can just ignore them. So we have a slave AXI high performance 0 port, which, shit. I goddamn hate this. Great, looks like we have completed the wiring. It took like 1.5 hours, I can't believe that anyway. We're done. You said all of that morning sign. Yeah, you just ignore the one second out. Are we done? Seriously? Great. So since we have made a new port, we will run connection automation again. I think it worked. Yeah. So it seems that we have completed our block design. If you have completed, you need to verify it. This icon kind of looks like verification, so let's press it. It will take a while. So if you run verification, it will complain with tons of warning messages. If you read that it is not assigned to an address range. And as I just mentioned, AXI devices are connected as an MMIO. If you do not know what an MMIO is, just like ignore it. But anyway, the point is that we need each devices, the DMA and FFT, to take up some space in the DRAM. Honestly, the memory space is different from the DRAM, but like this to be with this DRAM. So let's press OK. And if you go to the address editor, you have unassigned memory regions. Just right click on one of them and assign all. Boom, it's done. Very easy. Assign all. Great. Let's validate the design again. If you validate the design, it actually complains that T data, whatever. But the reason for this warning is that if you actually look upon the SAXI config, you can see that the config T data is actually 24 bits. But unfortunately, the AXI interconnect IP only supports 32 bits. So that's the warning, the reason for the warning, but we will just ignore it because it works anyway. Okay, I think we're done. We're done, finally done. So if you go back to the sources, is everybody done with validating the design and assigning the memory address? Okay, I'll wait. Okay, so going back, we made our design, okay? So if you completed our design, this is a block diagram, which is a bunch of blocks. We need to make this bunch of blocks into Verilog. Verilog meaning the hardware description language we learned in digital logic course. We can do that by clicking here. Right click on this. You can see a create HDL wrapper. After it's done, you have the design one wrapper dot verilog. Boom. We have generated this automatically. So great, seems it's working, we're done. So if you want to program this Verilog code into FPGA, we need to make it something called a bit stream. It's basically the same as the compiling in programming languages. So if you look at here, the generate bit stream is actually composed in multiple steps, such as synthesis, implementation, and whatever. But if you just press the generate bit string, it will do all these steps automatically for you. So first, read the HL wrapper, and second, press the generate bit stream. Just press OK. OK, and it will take like 10 minutes to finish. So 10 minutes to finish, great. Okay, so we see that our design is done, implementation is done. Well, you have multiple choices, and if you open the implemented design, you can see how much utilization. As I told you, FPGA is set on programmable arrays, and the maximum capacity is fixed. So we can actually see how much portion are we actually making use of it. I can't believe that this is so slow. Anyway, we actually have some leftover spaces. So if you actually implement your design, you need to evaluate your design. And we will not go very details on it, but do you want to see that what's the maximum timing? So I actually forgot how to see the timing, but oh, that's nice. Actually, if you see the clock summary, our design is actually at 100 megahertz. If you have a nice design, meaning that if you write some nice code, you'll be able to reach higher clock frequency. If you do not, it will result in a lower frequency. But since this is the default IP from Vivado, we can easily achieve 100 megahertz. So our hardware runs 100 megahertz. That's nice. And one more important thing is to see, if you go to reports and go to place design, you call it PD, you have the utilization. Okay. These are the programmable resources we can use on the FPGA board. And we are using, I don't know, 14%. Basically, if you have a bigger design, you can make the performance better by, I don't know, increasing the DMA size, increasing the bus size, increasing the FFT size, or whatever. Okay, anyway, I think we are using a pretty small design. Everything kind of fits here, so we are done. So if you're done, it's actually time to actually use our design. So, as I mentioned you, normally if you make a custom module, you need to write a bunch of C code in assembly to make use of it. Like, it's almost like reprogramming Linux, but we don't want to do that. Instead, we can use Python. And how do we use Python on our boards? Where in our lab, we have already installed some of the boards there, and you can actually access them using the UNIST Wi-Fi. So this is actually our pink board, and the Jupyter laptop is running on the ARM cores. Is everybody done looking at the report and so on? So, okay, just attention, please. We do not have enough boards to give it individually to each person. After this course ends, the TAs will assign you randomly to choose which boards you can use, okay? So right now, I will do this. Just look at this. You will have a chance to do it yourself after this session. So just look. So if you log on to the board, can see the Jupyter laptop running. And then see, this is actually running Linux on it. This is the FPGA board running Linux. And if you want to use your custom hardware, you need to first program the FPGA. And how do you do that is that you need to upload the generated bitstream. So I will just create a new folder. And inside the folder, I need to upload 2 files. If you see the project folder, you can find the bitstream in runs, implementation, and you have this design1 wrapper.bit, which is the bitstream file, which will be used to program your device. You can download this. Runs, implementation, and you have bitstream. Yeah, great. Why is it not working? I have no idea. Okay. Since we are using this as a Python kind of overlay, we need to upload another file which corresponds to the block diagram we have just made. You can find the diagram somewhere. Sources board design1 hardware handoff, and you have the design1.hwh file. You basically upload 2 things. First is the bitstream.bit. Second is the top level diagram, which is the hwh file. And one trick is that you need to match the name. And then I'll just simply create a Jupyter laptop file. And let's start programming. I believe everybody in this classroom has experience on using Python, right? If not, why the hell are you here at UNIST? Okay, so since we are using the Pink device, we need to import some packages from Pink. And then since we are using FFT, I will also import NumPy. And because we're using DMA, we need a new method called allocate. What? Okay. So if you see that we have made the design1.bit, and we can actually use this to load the design. So let's say our custom hardware is overlay, which is, what was it? Design is design1.bit. If it's done, you actually program the FPGA device. If you want to see whether the device is programmed correctly or not, you can make it, and it will tell you that, oh, your hardware has 3 DMAs, which can be seen by the CPU using the AXI interconnect, which we have mapped the memory regions for 3 DMA devices. So the first DMA 0 correspond to the data out. And the second DMA1 is the data in for the FFT device. So I will just make some simple like variables of something like FFT data in. Great. And let's see FFT data out. Oh, we have the DMA. So if you want to use the FFT device, we have a config register, right? We need to configure the FFT to work properly as we imagined. And if you, I actually forgot the location, but oh, you see, the config data is 24 bits wide. And the last 5 bits, we can use it to program the device to do a n-size FFT. So let's say we want to do like, I don't know, 1024 numbers of FFT. And let's say n is equal to 1024 and log n should be 2 to the power of 10. I think this is a bad idea. Something like this. And then we can say that we want to program the FFT IP to work as a 2 to the power of 10 FFT. And this kind of configuration and all the data transfer will be done using the DMA. So in order to use a DMA, we need to first make an array in Python. So let's say in buffer, we'll just make a buffer to handle the input data. We'll use the allocate method of ping. The shape should be something like endpoints, right? And we also need to explicitly state the data type. I'll do the same for the config buffer and the output data buffers. And we want to generate some sample data to fed inside the FFT. I'll just use NumPy to generate random inputs. How do I use randint? I forgot. Actually forgot. Oh, okay, it works. So first, before we use the DMA, we need to set the right config. So I'll just say config buffer 0 is n. So we just put the size of the FFT at the least significant bits of the register. If I'm going too fast, don't worry. We will give you time to do this yourself right after this. And if we just made the config buffer, we store the data in the buffers, and we will actually initiate the DMA to send the data from the buffers, which is currently inside the CPU, to the FFT. We can do it by FFT config dot send channel dot transfer and the config buffer. And always, if you want to use a DMA, as I told you, the DMA will send a signal to the CPU saying that, hey, I finished our job. So that we need to wait until the DMA finishes. This can be done by FFT config dot, send channel dot wait. Wait. Well, I actually kind of sent it twice, so I think it's making an error, but let's run it again. Okay, if it does not work, I actually made a mistake on this. If it seems that it's not working, and I actually don't know why. Oh, it works, yeah. Sorry, I uploaded the wrong file. So it seems that send channel.wait kind of perfectly works. So it means that we have programmed the device, and now we need to do, we need to actually send data. So we will going to same. My bad. So how can we do it? We can do something like in buffer send channel dot transfer, and we need to choose which array we should transfer. And I believe it should be, oh no, sorry, not the in buffer, the FFT data in. And we will be transferring the in buffer. And in the receive channel, which is data out has the receive channel, dot transfer out buffer. Before we actually launch our hardware, let's see what is inside the out buffer. Okay, so currently the out buffer has nothing inside. But when you launch this, we are going to expect we have some output data inside here. So we'll just make two waits. Then channel data out, receive channel.wait. Let's see. Have I mistaken this again? Data in is DMA1. Let's see. I can't believe that I restarted and it's working now. Oh my God. Anyways, seems it's working. So let's see. So before we actually put something in the info, we didn't put anything inside the in buffer. So I'll just like put something. So we can do it something like mp.copy to FFT sample, and we'll copy the data of the FFT sample, which is just the random numbers, and we'll put inside the FFT in buffer. Let's see. So out buffer, we have nothing here. In buffer, let's see. We have nothing. What? Why are you doing this to me? Oh my God. Hey, did I make this opposite? What on earth am I doing it?
Destination and source.
The original one was correct, right? No?
No, this is correct.
This is correct.
But we have lot.
Oh, wait. In buffer. Yes, that's correct. FFT sample. Sorry about that. Okay. So FFT sample, we have random numbers, and we will copy the FFT sample into the in buffer. And in the in buffer, we have, oh, nice. We have the random numbers. Currently, the out buffer has nothing. And if you launch the DMA, I don't see why it's not working. Let's run it again. Oh, great. It works. It used to be 0 back then, and we have some data right now. So, and it's not working again. So I could have possibly messed up with the weight things. Let me just try it once more. And it's not working. So I think I possibly messed up with the block diagram, or we just set up the wrong board. Min-sang, do you know which board we're using for? Wait, that's a good question. DMA is asynchronous, meaning that the DMA does the copy by itself. At the same time, CPU does not have no information what kind of thing it's doing. So when the DMA finishes, it needs to tell the CPU that I have done my work. And waiting for the DMA to finish is the wait. Okay, we try again. New board. Okay, get started. So let's go fast. Import from pink. Import overlay from pink. Import allocate. Import numpy as NP. And what should we do? First, will be something like overlay, and it was the design 1.bit. And it's working great. We have 3 DMA channels. And for each channels, let's say FFT data in is the custom HW dot, what was the name again? It's AXI DMA 0. FFT, is it? I actually forgot. I don't know. This is like guess. Data in should be custom hw.axi DMA. Wait. No, I don't know. Like AMA DMA 2. No, sorry. 1. AXI DMA 2. Please work. And we need to make buffers for each DMAs. Config buffer is allocates size. How do you run it? Size shape is just 1. We will just put a simple Scala value, and the D type should be uint32 because it's 32 bits. Oh, damn, knows. and the D in buffer, and the D out buffer. Insert. D should be shape of n, and in this case, we want to set log n to be 10 and n equal to the 2 to the power of log n. I think this works. If you see config buffer, it's just 0, D in buffer, it's also 0, D out buffer, also 0 is great. And we need to make a sample FFT random numbers, which is FFT samples or np.random.rand int. Just like make shape is equal to n, and the d type should be np.uint32. Now, if I see FFT samples, okay, I have an array of uint32 values. Seems good. And what do we have to do again? Well, we first need to configure the config buffer. So the config buffer 0 should be n. And we look at the config buffer again. Okay, we have. Oh, I should have put log n here. That's why I was wrong. Oh my God, I can't believe that. Yeah. Oh my God. If you see, the data should. Oh, okay. Sorry. Now I have figured out what I was wrong. Okay, let's go back. It was which one? Yeah, this one. Let's try again. It should be logging, right? I made a mistake. Yeah. This should be written in log n. And I just write 1024. That was the problem. So what is wrong here? Did it crash? Restart. Okay, it's done. Assign 1, blah, blah, blah. 10. Yes, we have 10. Okay. And we have nothing on the out buffer. What did I do wrong? This? Okay. Now we are ready to run this. In buffer, we have some dummy data, random numbers. Output buffer, we have nothing inside here. And let's run it. Nice, we have some values. It's working. Thank God. If you run it again, it works. Okay, so I just messed up with the config. So this is what you need to. I haven't looked details in the datasheet. Sorry about that. And if you want to measure the time, it's actually 345 microseconds for a 1024 sized FFT. And if I measure the time for a CPU, oh no, sorry, FFT. Oh, it's 657 microseconds per loop, which meaning that our hardware is almost twice faster than the CPU, correct? But let's see, if I change the length of the array into, let's say, the maximum was 14, right? So output first reset it to 0. We need to put some more data here. Okay, we have increased the length, meaning that it should take longer. So let's run it on CPUs. It used to be 657 before. It takes quite a long time. It takes 13.8, which is how many times? 220 times, 200 times? Very slow. How much time? 345 microseconds. 471. How is that possible? It didn't change. Okay? So if I change this value into a very small sized FFT, for example, like 4, the CPU takes 291. Our hardware takes 348. Meaning that actually a 1024 size FFT on hardware is actually take the same time to do a 16 size transformer hardware. It's your homework to see the time complexity of the FFT algorithm comparing the version on CPU and the hardware. So let me give a demonstration. The time complexity of the FFT algorithm is n log n, meaning that if you increase the n size from 1 to, I don't know, 16K, the runtime will go up something like this. Question, how would the hardware runtime look like? 01, exactly, correct. It should be flat. It should be flat like this. And why is it flat? Well, because it's a hardware. Like, it's not a software. It's not an algorithm. You just put the data inside and get out, and it will take the constant time. But you see, when you increase the point to 16K, naturally increase the bit. In reality, you should do it yourself, and in reality, it will go something like this. Do you know why it takes longer and longer inputs? The computational time would be the same, but why does it take longer on longer size inputs? Memory bound, exactly. It takes time to transfer memory. And if you want to solve the memory bound problem, what will you going to do? Increase the bus size, exactly. So this is what I wanted to demonstrate today. I guess we have around 20 minutes to do this by yourself. Where's Minsa? Minsa? Okay, so how many boards online? Five. So 1, ready students next time. 2, 3, 4. Okay, so 1 board here. 2nd board here. 3rd board and 4th board. How about that? I think we can use that over for now. Let's just use 4 boards. The address is, what's the address? 84. Okay. 114. 17. 9. 24. And 1980 until 1984. 1980, 1981, 1982, 1983.
And I know that it's possible to unload the virtual brain. You would quickly care about the running those, right?
Yeah. So the board is an FPGA board, so we cannot run multiple FPGAs at the same time. So you just take turns in your group to just try with one version, okay? I know that since I don't know that the names of Blackboard, that's for today's homework. You can use that name for today's homework. Right now we'll just use 1980, 1981, 1982, 1983. Am I correct? Okay. The board password for the board is dialects. All small case. Okay. You download two files. First is the bit stream. Bit stream. Attention, please. Just a second. Mingo. At the runs implementation, you can find something called a bit stream, about bit. Did you find it? Find it?
I see the past of the
Yes. And the second file is the HWH file. You can find it inside sources 1, board design 1, HW handoff, and you can find the HWH file. Okay, the course is scheduled until 4:20, which means that we have 22 minutes left. I will announce the assignment right now. So we uploaded this example code here. And what's lab? Okay. So this DMA012, you need to figure that out yourself according to your board design. Everything else will work. And we actually have homeworks. The first homework is that we will. So you need to submit three or four things. First, you need to submit the reports. We don't expect you to write a high quality reports. Just paste some graphs and write some word, and that's all it. First report. Second, you need to submit the bitstream file and the HWH file. And third, I forgot. Anyway, you can go backward. And at the report, you must answer these questions. First, make a plot of the runtime comparing CPU and GPU, just like this, right? And secondly, try to answer why the reason you think that the time complexity of hardware looks like that. And the third homework could be a bit difficult or not, but we haven't actually verified where the Fourier result is equal to the CPO or not. So, double E students. Okay, computer science students, raise your hand. Like 1, 2, 3, 4. Do you guys have an idea what an FFT is? Okay. One tip is that if you take an array and do the Fourier transform, and you do the inverse Fourier transform, it should go back to the original state. Double you guys know that, right? So you can test whether the FFT is correct or not by just doing 2 FFTs. And how you can do both forward and inverse FFT by changing the config register, which you can find it here.
Config, where the hell is config?
Yes. If you set these bits to 1, you can choose whether to do the forward or the inverse pass. And everything else is just kind of optional. We need to change 2 things: this form and the FFT size of the FFT. And you must know that our hardware is using a custom floating point, fixed point format. Does anybody know what a fixed format is? You can search it and believe me, it's not hard. So basically, if it's a fixed point format to store complex numbers, meaning that you have a 32-bit number, you divide it by 2 16-bit numbers, and you multiply the scale factor, and you can convert it into complex numbers. You should do that on your homework. Okay? Does it make sense? Am I clear? This week, homework is individual homework. We don't have group projects right now. You can see the Blackboard to see which kind of server you're using. If the server crashes, you may contact ETAs, and we will go to the lab and turn it off and reboot it for you, okay? Okay, so this is the homework. Try to run the examples and see you next week. Great.